take over since we don't want to waste any time. So
Thanks. Sorry to be rushing.
Zach, for preparing and getting us up to speed.
Yeah, so I'm going to talk a little bit about a project that Lucina, Jason, and I worked on for a couple of years, along with Salome, who was a visiting researcher back in Miami. And then so that'll be the first bit. The second bit will be about some thinking about brain signal variability that I've been doing recently with Jason and others. So it'll be interesting to get anyone's thoughts at that point as well, but feel free to stop me if there's any questions or anything like that. So to start off with, I'll talk about brain signal variability and its relationship with executive functions. I've been fortunate in that Celia gave a great talk a couple of weeks ago about executive functions, and Jason is like our residential expert on brain signal variability. So everybody's probably pretty familiar with all of this stuff. So I'll keep it pretty brief in terms of recap. When I'm thinking about executive functions, I'm thinking mostly about sets of abilities that are involved in kind of governing other cognitive tasks. I often go back to the analogy of executive functions as the conductor of an orchestra, where the orchestra has other cognitive capacities, and the conductor executive functions role is in regulating other cognitive capacities in kind of overseeing and keeping control on different impulses and so on. So I typically think of these three broad categories: cognitive flexibility, like the ability to go from one task to another, or to multitask, or to switch mental sets; inhibitory control, which is that kind of inhibition of impulses, downplaying those knee-jerk reactions to instead elicit or respond with something more thoughtful or more deliberate. And then working memory is the ability to keep things in mind and mental capacity while working with it or related information, keeping it in attention. And we know that these, broadly speaking, executive functions fluctuate across the lifespan. They take 20-ish years to come online, and then they are plateaued throughout adulthood and decline in older age. To jump ahead to some of our data, we see these same patterns emerge, just demonstrating that executive functions really do have this quadratic type of nonlinear relationship. So this is a whole host of different tasks that I used in my study. Tasks of cognitive flexibility, of inhibition, working memory, and processing speed. And really across these several tasks, we see that in early adolescence, these executive functions are still improving, and then they level off between about 35 and 60 or so, and then we see declines in later adulthood. For simplicity, every task is coded such that a higher score is better performance. Even though that may not line up with how these tasks are typically scored, I just wanted to keep interpretations consistent. All right, so back to brain signal variability. Speaking broadly, the hypothesis with brain signal variability is that more variability would facilitate more flexibility, more adaptability at an individual level. So somebody who has more variability occurring in their brain, just speaking very abstractly, they're going to have a higher potential to engage in different cognitive tasks because of that variance. Some work by Doug Garrett, along with Jason and others, have shown that there's associations between signal variability and age, as well as signal variability and cognitive capacities. Although most of these studies have been done looking at just a single age cohort, so like older adults or at middle-aged adults and so on. And we see there are some associations with basic abilities like psychomotor speed and processing speed, simple attention, but also with cognitive flexibility in middle adulthood. And we know that brain signal variability shows a similar kind of trajectories to executive functions in that it is at the least decreasing into older adulthood. So we see declines throughout the lifespan in brain signal variability. So then our thinking going into this study was that there may be some interaction or association between age and brain signal variability that's contributing to the changes we see later in life, at the least with executive functions. So maybe brain signal variability is underpinning that decline, or maybe it can be used to offset some of that decline. So we haven't also seen investigations of brain signal variability at a network level either. They tend to be either regional, focusing on one or two brain regions, or whole brain variability. So across the entire cortex, how much variability is there? But I don't know of any, off the top at least, that have looked at it really at this network-based level, where we're looking at the default mode and the central executive. And where in particular, I would expect at least the central executive network to be most implicated with tasks of executive function, just given its association and task-based fMRI. Okay, so as it relates to variability, there's a couple of different ways we can think about what variability is. And I know everyone loves a good statistics formula, so here's two of them for us.
Oh, hang on, I just had to unmute so Jason could ask a question. Yeah.
Oh, yeah,
Later.
I can't hear.
Oh, so, I guess, and maybe just explain, not everyone is aware, but you're talking about like for every single voxel, there's a time series, and you're talking about the variability of every single voxel's time series. So you could, in theory, compute the variability for all 100,000 voxels or something in the brain. That's what you're talking about?
Right, yep. So it could be at the voxel level, and looking at the time series for a voxel, how much variability do we see in that time series? But as far as I thought of, and we'll wait to see what reviewers think, I don't know of why that wouldn't generalize to like regional variability or network-based variability. And I know that others have looked at whole brain variability. So looking at across all voxels, how much variability is there? Did that answer the question?
Yeah, it's just like basically, it's more variable if the blood flow is bigger, like a bigger wave. If it's tiny, then it's less variability. So that's all I'm interested in.
Yep, thanks, Jason. And then more specifically, so we can think of different ways of quantifying variability. I'm going to lean very heavily on Jason's explanations for the difference here. So feel free to jump in, Jason, if you want. But when we're thinking of standard deviation, this is the most typical form of variability we use in statistics. The caveat or the limitation of standard deviation in this capacity is that it is agnostic to the time series, such that if we randomize where the data are occurring in the time series, the standard deviation would always be the same thing. In other words, it's not taking into account changes at a moment-to-moment level. It's looking at just across the whole set of data, how much variance is occurring. On the other hand, we have root mean squared successive differences, or how I'll probably just refer to variability moving forward, where this is taking into account the difference from one time point to the next time point. And so it's looking at changes at the time scale level as opposed to just overall deviations. I don't know if other people think in terms of formulas, but this is encapsulated by the differences between means. So that's what standard deviation is looking at, is how far a data point's different from the mean, as opposed to the difference between one time point and the time point before it. So it's that moment-to-moment based differences. So these are both ways of thinking about how variability is manifesting. And then we've decided to go with the MSSD because it is considering how much change is occurring at a moment-based level as opposed to just overall. So one limitation, though, of variability, not just MSSD, but any form of variability that we've looked at, is that the regional variability of one region is highly correlated to the rest of the brain. There's a high overlap in regions in terms of their variability with other regions. And this, it probably makes sense. Somebody who has a more variable, I don't know, frontal lobe also has a more variable like occipital lobe. There's just more variability occurring in that person. But where this is problematic is if we're interested in any kind of statistical differences, these are much too highly correlated to be included in a statistical model together. There's just too much overlap in their variance. So what we came up with for this study was adjusting the regional MSSD values based on whole brain variability at that same time point. So regressing out essentially whole brain variability from each of the regional variabilities. And what we end up with is a much more orthogonalized version of network or variability across the brain. So you can see in this last column here, each of the major brain networks are essentially uncorrelated with the whole brain's variability, if we calculate variability across every voxel. There's still a decent degree of overlap in these networks like the central executive and default mode, as well as in the salience network, whereas other networks are much lower in magnitude of correlation with networks. So the idea behind this approach was to really separate whole brain variability from regional variability. Now we can include both of those metrics, or all of them, in a single statistical model to see, is it just having a more variable brain predicts better executive function, or is it variability specific to one brain region that's associated with executive functions? Nope, kind of went ahead of myself there. But so going into the study, we were asking that first question, is network specific variability associated with executive functions, as well as are the associations between executive functions and variability consistent across the lifespan? Or do we see that variability might be a beneficial thing in middle adulthood, but in later adulthood, it might be harmful because it's interfering with cognition or something like that. So to do this, we had a pretty large sample because we used the Nathan Klein Institute, which has like 1,000 people in total. So we had 724 adults people ranging from 8 to 85 years. It was a pretty comprehensive sample. They underwent a complete cognitive battery. So as it relates to this study, I looked at the Dellis-Kaplan executive function system and the computerized neurocognitive battery, both of which have a whole range of executive function and related tasks. And then they also completed a 10-minute resting state scan. The tasks were not completed in the scanner, so it's not a task-based fMRI in any regard. All right, so there's a lot of data that came from all of these questions and all of the networks and whatnot. So I'm really just going to focus in on what I think are the interesting bits. The most consistent relationship that emerged is whole brain variability is pretty consistently related to executive function tasks. The first two tasks, the TMTB and category switching, these are cognitive flexibility. The next two are inhibitory control, and then the last two are processing speed. And there's pretty consistent association with whole brain variability across all three of those executive function domains. What's more interesting is if we look at these effects by age, so we treat age as a moderator, we see the association between variability and cognitive performance is positive for older adults. In other words, whole brain variability is a good thing when you're older. Whereas with younger adults or those in adolescence, there's either no relationship between variability and task performance or a negative relationship, such that more variability is harmful to one's performance. So there does seem to be some positive benefit, at least for older adults, with having more variability, potentially maintaining some of those cognitive functions we would expect to decline. Now, when we look at it more specifically by regions or networks, there's not quite as exciting of results as I would have liked, but we do see some networks making a presence. So the default mode is associated with the cognitive flexibility and inhibitory control, one task of each, and processing speed generally. And what I like when I'm doing statistics is to see that we're seeing the same kind of relationship emerging across several tasks, which gives me a little bit more confidence in the findings. Again, we're seeing that in older adulthood, more variability is associated with better cognitive performance. And then in adolescence and early adulthood, it's essentially a flat line, so no relationship between variability and executive functions. And then the one network that has the opposite kind of relationship was as it relates to limbic network, or I don't know if that's common to refer to the limbic system as a network, so regions of the limbic system. Is such that older adulthood, limbic variability in older adulthood was negatively related to task performance. All right. I saw unmute. I'm not sure if there was a question or.
Did you have a question?
Yeah. Were the tasks correlated?
Were the tasks correlated?
Yeah, with each other?
Yeah, they are correlated with each other. That's a good question. I didn't look at how intense that correlation is, because we would typically use all of these like clinically and not think of them as interchangeable. But yeah, I'm not sure how strong that correlation is. What's your line of thinking there?
Well, that would explain why they're all the same, right? They're all highly correlated.
Right. Yeah, I'll have to
Well,
look
they
at that.
should
I'll
be.
have to see how high.
A lot of them are under the executive function umbrella, so they should be correlated, I would think.
Yep, I would agree. They should be correlated. They probably are, but I do think it's going to be moderate. I'm going to guess like 0.5 would be the higher end, maybe 0.6, but not so much so that they're like interchangeable statistically. That's my guess. All right. So just to summarize, we see whole brain variability is the most consistent indicator of executive functions, and also consistently that whole brain variability is a positive thing in older adulthood and either harmful or of no effect to those in adolescence and middle adulthood. The default mode was more specific, and the limbic network really were more specific to processing speed, although there were those associations with one task of cognitive flexibility and of inhibitory control. And it seems as though this is generally a positive thing for older adults, although this is all cross-sectional. So it could be the case that it's just our older adults who have survived to this point, or these aren't necessarily changes over time. So there's a lot of caveats as it relates to those conclusions. Okay, so that was the first study that we have currently under review. So we'll see how people feel about some of the decisions we've made there. But I wanted to talk about. Oh.
Sending that, Zach. Where did you
Sorry?
end up sending?
Oh,
Where'd
where
you
did
end
I
up?
send it to? I haven't resubmitted it since the neuroimage change. I wanted to submit it to, was it human brain mapping, but I have to figure out the like visual abstract and not doing it, like how to submit without doing it.
Okay, you can either submit to human brain mapping or network neuroscience, either one of those.
Oh, okay.
Yeah.
All right. Okay, so then this next project is a work in progress, but I think it's an interesting kind of conversation to have around what variability is. And this current project came from trying to understand how normalizing the time series influences the final product that we get when we're calculating variability. Because my hypothesis when we've been having these conversations is that it really shouldn't make a difference if we use raw data, if we use standardized data, if we center the data. It should all get us to essentially the same result. But we're seeing empirically that that's not necessarily the case. So we started trying to understand what is it that's happening during this normalization process that's leading us to different values for variability.
Oh, that, what did you do for that last one? Is it just raw?
Sorry, Jason, one more time.
What do you do for the topic you're just talking about, raw time series, or you use for it?
Right. Oh, so for the one that we already did, it was centered, but raw metric, so not standardized.
So that should be perfectly correlated with the Z-score one?
Yep.
Okay.
Well, it should be perfectly correlated with the raw score. I'm not sure why, but it wouldn't be perfectly correlated with the Z-score metrics. I'll show you that piece in just a moment. I think it'll make more sense, hopefully. Okay, so as Jason, I think, was explaining, as it relates to variability, what we're asking is how much change is there occurring across this time series. Something that was like really close to the mean would be low variability, whereas like high peaks and valleys would be high variability. And what we're seeing is, depending on how we normalize the time series, the final result we get when we're calculating MSSD is pretty different. If it's raw or centered time series, it's perfectly correlated. We get the same result. If we Z-score it, I would expect to see the same thing we're seeing with raw and centered, just based on what a Z transformation is. However, we're seeing it's uncorrelated with the raw unit MSSD. And then we have percent change being somewhere in the middle, where it's about 0.7 with raw units and then moderate 0.2 or so with Z-scored units. And this is just, so what we're seeing here is across the whole brain. So to break down what this looks like, the first three time series here are if we use the raw time series, centered time series, and then a Z-scored time series. And at this point, at the time series level, they're perfectly correlated. Now, if we use percent signal change, the last option here, then we see it's pretty much uncorrelated with the raw time series. I think it's 0.1 or so, if memory is serving. And that is because the time series undergoes a significant transformation with percent signal, and that now every time point is being considered relative to the prior time point. And while the time series are the same, if we go down the steps of calculating MSSD, this is where we start to see some differences emerging based on the normalization method. So this is kind of a lot. On the left here, this is each step of calculating MSSD starting with the time series. And we see raw, centered, and z-scored time series are perfectly correlated. There's no difference. If we take the percent change of the raw time series, that's going to give us a different result than if we take the percent signal change of the centered or the z-scored time series, which are different than the others, but identical. And then when we go through each of the steps of calculating MSSD, we see the raw, centered, and z-scored normalizations diverge from each other when we sum the successive squared differences, which is essentially when we go from, I guess, wide as it relates to the time series to when we sum that time series up, then the z-scored units are no longer correlated with the raw and centered units. They're actually almost perfectly uncorrelated, which is impressive. However, raw or percent change centered and percent change z-scored units stay perfectly correlated all the way through. So there's some difference at this step where the centered and z-scored are separating in raw units. They're not for the percent signal change. I have no idea what this means yet, but this is where we're currently at with trying to understand why each of these steps would make any kind of difference from one normalization method to the other. So yeah, that's where I'll stop for the sake of time. Sorry, that was kind of quick, but.
I know you have to go real quick, but is it the case
come
that most of the previous literature has relied on standard deviation? And so we're trying to figure out what the details are for optimizing the MSSD. And there's just not that many papers out there that used MSSD. Is that true? Or
Jason, jump in if I'm wrong here, but I think MSSD has been used by those people who are looking at variability, but even that like group is pretty small. I don't think this has typically been considered noise in the data, and that really we're not interested in.
but like Garrett's papers are almost all SD, right? Almost most of Garrett's papers are SD. Is that true? And he's the only other main person.
Yeah.
I don't remember that specifically. Jason, do you?
Yeah. So the thing was, Doug Garrett was one of the first ones to do this, and he also looked at standard deviation. But he also looked at MSSD. But Doug Garrett does a percent change. No, let's see the percent. Whatever Doug Garrett does, SD and MSSD are exactly the same.
Right.
But,
so
but if we do some of these other things, then MSSD and SD aren't really.
Yep, exactly. So
Sorry.
no, sorry. I think it's just delayed. I was just going to say that I tested that theory, and when we do percent signal change, MSSD and SD are identical, and that's because when you're calculating percent signal change, you're already bringing in the moment-to-moment differences. That's what makes it a percent change. So you're doing the same thing. It's just at a slightly different step. You're taking those differences. So it makes sense mathematically.
Yeah, if you want to bring up that last slide.
Oh yeah.
So what Zach was showing here is how MSSD changes across all these. There's really supposed to be another, well, there's going to be. That's gonna have fun. There's gonna be another side where we have S. And then that also changes all these things here.
That's what makes it hard to look at all the previous literature, because they use different normalization and different measures of variability. So we don't know if our study's results compare with the previous literature, because they might have used a slightly different pipeline, right?
And until now, it was assuming that it was all just the same, like Zach said. Because Doug Garrett did just one version. And nobody else thought any differently of it. So
Yeah.
here we are.
Well, I know you have to go, Zach, but thanks for giving us that quick overview. We'll catch up with you and discuss in greater detail. Thanks.
Sounds good. Yeah, sorry to run, but thank you all. It was fun. See you guys soon.
Thanks, Zach. And for the rest of you who are still around, we can take some time to go over what projects you're working on and stuff like that since we're here. Zach had to leave early, so we let him go first, but maybe we can get some updates, like Charles, for example, if you want to give a project update and just let us know what you're working on.
Yeah. So I'm just working on the cognitive flexibility paper. It's going great. Just kind of like editing the figures that I have now to basically show a little bit more. And then working on my proposal for my dissertation. I got my first kind of like aims laid out. I'm really now waiting for them to put me on the IRB so I can actually see the data. So I'm really kind of just waiting on that now. And then get the entree ready for the CIML symposium.
Great. Thanks, Charles. What about Yunkai? What are you working on?
Yeah. Can you hear me? Because okay, great. Because my Mac has little problems. I'm currently doing some like trying to create a toolbox which is called a genetic algorithm based spatial decoding toolbox. And we're based on Jason's advice, we just compared that toolbox with some traditional tools we used before, like the traditional global SVM and the MBS toolbox, compared with them. And I just organized all the data, and I'm now writing the paper, trying to summarize all the results. And and a couple of weeks ago, I'm focusing on some like a speech perception decoding work, and that work is currently under the review of the Journal of Neuroscience. And yeah, that's it. Hope I can talk a little more about the decoding work. Yeah.
Yeah, that's great. Congrats on the paper under review.
Thanks.
Good. How about Lane? Can you tell us what you've been up to? If you can hear us. Lane. All right, we'll get back to whoever's in the room here. Jordy, any updates?
Yeah, I'm just continuing to work on my Agentic project with BCCL and continue to track subjects and have the conference in May.
Oh, good.
Yeah, and we have to submit our draft thing by the end of the month for one of the conferences.
Is this for a poster?
Yeah, for the poster.
Great, all right. We'll look forward to seeing that. Oh, Ashley?
I mean, I'm just organizing some data that Lauren sent me. It's for her manuscript, so it's just like organizing the tables and stuff like that.
Great. All right. Yeah. Bertha?
I'm working with audience. We have like 3 poster presentations coming up.
Mhm.
Yeah. So
Great.
yeah. So previously I was working with so it's the same anxiety project that I am talking about here. So I tried doing analysis using FSL, but then we tried smoothing the data to see if we get any better results in that, but it seems like it's just showing different results altogether.
Was that also with MSSD?
Yeah,
Yeah.
this one is with MSSD.
Mhm.
So now I'm like trying to use PLS. I've been like trying to run it again. It stopped on Huffman, and I've been like trying to run it again. And then also we were like thinking about on AlphaCell, like it runs a linear regression model. So we were like thinking of quadratic. So I was like thinking maybe I could use some help from stats department and stat people that we have in the group to discuss how to interpret it.
Okay.
So yeah, I got 2 interesting results coming out. Hopefully those are interesting, but yeah, we'll talk about that.
Good. Yeah, you can talk with Zach and Taylor about
Yeah.
the quadratic thing to see if it's something you can implement.
Yeah.
Great. Updates?
Hello. The global signal paper is, we're gonna submit that soon. And then working on some retests, reliability of this variability metrics with Hookie and all that.
Well, yeah, well, Bianca, if you're wanting to check in with Jason and Zach and Hopi, they're all working on MSSD now, and you've heard about some of these pipeline things, so maybe it matters, how its data is normalized and all of that,
Yeah.
so good to check and see, if they have any recommendations for that, because it looks like it makes a big difference in the result, depending exactly what the steps are.
Yeah.
So, good. So I guess, yeah, for us, in the lab, we're gonna try to go out to lunch on Wednesday for anyone who's around. So if you want to join up, we'll just meet in front of Semel at 1 this week on Wednesday. I'll be at a conference in San Diego next week, so I'll be Zoom for whatever meetings there are. We'll have one of our former grad students, Casey, present in lab meeting next Monday while I'm gone. So that will be a good chance to check in with someone she's now an assistant professor in Minnesota. So she'll be good to chat with. And we're going to do a combined lab happy hour with Adriana Galvan's group. That's the group that Charles is working with on the anxiety project. So and Paula is in that lab, and Katie, the other postdoc who works with us, is also in that lab. So we'll do a combined happy hour with them on May 8th. Are there other things coming up? When do classes end here? Is it June? Middle,
Classes and.
June 12th.
June 12th, yeah, middle of June. Okay. Wait, what is it now? April? Okay.
Yeah.
You still got, yeah, okay, we still have 2 months, all right. I have to figure out what the quarter schedule is. We also have, we're doing the neuroimaging affinity group again, so that's every other Wednesday at 2:00 in the Gonda. I've been forwarding those emails, so that's a journal club where we discuss different papers, so if that fits in your schedule, you can come to that. Lauren is one of the organizers of that journal club. I'm the instructor of it for this quarter, so we meet every couple of weeks.
Would you say it's for NUS?
Sorry?
What club is it?
It's the neuroaffinity group. It's a journal club.
Oh.
Yeah, so like we discuss recent publications and just like talk about the results and, find flaws in the papers and stuff like that. So,
Okay.
so yeah, that's it's a graduate level course, but anyone's welcome to attend. It's just like a small group of people. So the first meeting happened last week, and it's every other Wednesday. So it wouldn't be this Wednesday, but it'll be the Wednesday after. So you'll see the emails for it. I think that in the email title, it says NAG, like neuroaffinity group, neuroimaging affinity group. So if you want to come to those meetings, you're welcome to come and, yeah, everything I'm talking about is all on the lab Google Calendar. And the last thing is that we're going to hire a lab manager or a research assistant full-time to try to help us with our new study on bilingualism and autism. If you know anyone who's graduating soon and might want to work with us for a couple of years, especially if they're Spanish English bilingual and they want to work with kids with autism and they want a full-time position for 2 years, let me know, because we're trying to hire them very soon. Like someone who's, do you know anyone?
I've been passing it around,
Yeah.
yeah, but so far nothing back, but I'll keep looking for.
Yeah, we're gonna start interviewing some people. We already got 10 or 11 applications, but most of them are not Spanish English bilingual, so we might end up having to hire someone who isn't. If we can't find someone who is, essentially, but that'll be like the full-time person who works with us for scanning and scheduling participants and all of that. So we're hoping that we'll get that person in place by May or June, so that we can start the study in full swing, this summer. As you know, the scanner is going down April 21st, and so there'll be like about a week of processing and, upgrading. And then we'll all have to go back and do another scanner training just to look at the new system once it's up. But once you've done it, it's pretty easy to learn the new system. It's just there'll be slight differences. So then we won't start scanning again until May, at the earliest, because everything has to get back up and running. So in the meantime, hopefully we can help find a person to hire or interview some people. And
What was the pay again for this?
the pay is like 50,000, 50 something a year. So it's like a full-time researchers, 40 hours a week, 50,000 a year, or maybe 51,000 a year. It's like a good, full-time position for anybody. Basically, anyone who's graduating undergrad and wants like more research experience before they go apply for med school or before they apply for grad school, or or they just don't want to go anywhere for a couple of years and want to, so if you know anybody in like any of your neuroscience classes who's graduating and is trying to figure out what to do for the next 2 years, and somebody, who has like research interests and experience in research, feel free to forward the ad that I sent around. But yeah, we'll try to hire someone pretty soon. Any other announcements? Things going on? Okay, well, for those of you who are around, we'll see you at our lunch and our happy hours and do you have another undergrad meeting coming up or have you scheduled anything? Okay, nothing on the schedule for now. All right, great. Well, then we'll see you all next time. Thanks. Okay.